All right, the second method that we are going to talk about, this again is section 3.6, part 1. Second part we are going to look about is approximating using the trapezoidal rule. So if you remember back when we talked about trapezoids, the equation for the area of a trapezoid is 1/2 times the height times base sub 1 plus base sub 2. And so that would be a shape that looks like this, is normally kind of what you usually think of for a trapezoid, where you'd have your base sub 1 up here, base sub 2 down here, and then your height is here. And then this is the equation for the area of that object. So now what we're looking at here is we're going to break up our subintervals into trapezoids this time instead of into rectangles. So the height of our trapezoids is going to be this way. So our h is going to be equal to delta x. And then this side over here is going to be our b sub 1. And then this side over here is going to be our b sub 2. So the area for this first trapezoid here, our first area, is going to be equal to the 1/2 times the height, which is delta x, times b sub 1 plus b sub 2. Then our next one, let's leave b sub 2 here. Let's call our next height b sub 3. So we would have a sub 2 is equal to 1/2 delta x times b sub 2 plus b sub 3. Okay, and so that would be a sub 2, the area of our second interval. So, whoops, that makes it look like, that'll look fine there. All right, so our, oh, whoops, I'm still on erasing, there we go. Okay, so this one here was b sub 3. This line here is going to be b sub 4. So our next area, third area, is going to be 1/2 times the height, which is delta x, times b sub 3 plus b sub 4. Okay, and so forth. So if we want to put all of these together into one big area, we're going to use t sub 4 to represent that we are using a trapezoidal rule to find an approximation for this integration. The 4 means that we're using 4 subintervals. Every one of our little areas is going to have a 1/2 delta x, so we can factor that out. Factor out the 1/2 delta x. And then we just need to find the sum of all of the sides of our subintervals. But what we notice is the b sub 1 is only used once. But what about the b sub 2? The b sub 2 is used 2 times. The b sub 3 is used 2 times. And if I was going to go on and find my last area, you see that the b sub 4 would be also used 2 times. So it would be b sub 1 plus 2 times b sub 2 plus 2 times b sub 3 plus 2 times b sub 4. But then when we get to our last side would be b sub 5. And that would not be used twice. So only one time on the first and the last of the sides of our endpoint, or the endpoints of our intervals. Okay, so that is how we are going to use our trapezoidal rule to find the area underneath a curve. And so let's move on here. I'll show you what the definition looks like. Oh, well, here. Okay, so let's talk about this first. So this is a comparison. This is our trapezoidal rule over here on the left-hand side, and this is showing our midpoint rule on the right-hand side. And you can see it looks like the trapezoidal rule would be our closest approximation, but it's really, most of the time, is not. Most of the time, this midpoint rule is our closest approximation, because you always have a little bit of overestimation and a little bit of underestimation on every single one of them. But in our trapezoidal rule, we're always either overestimating. So see, when it's concave up, we are overestimating. When it's concave down, we're underestimating with the trapezoidal rule. So that's kind of what happens with our trapezoidal rule. The trapezoidal rule, however, is a little bit of an easier equation to use, and you'll notice that as you're going through these these questions in this assignment. So let's move on. This is the definition, formal definition of the trapezoid rule. So you can see they're finding the delta x the same way, b minus a over n. Find your endpoints. Our endpoints in this case, they are labeling them x sub 0, x sub 1, x sub 2, x sub n. And then when you go through finding the area using the trapezoidal rule, use a capital T, sub, how many ever of the intervals that are using, and then 1/2 times delta x times f of the first endpoint plus 2 times f of the second endpoint, and so on until you get all the way to the end. Notice that the very first function notation and the very last function notation are not multiplied by 2 because they are not used twice. If you go back through the first part of this video that we've done so far, hopefully you can see and understand why these middle ones are all multiplied by 2. Okay, moving on, let's look at example number 2. So this is the same exact problem that we did for the last one. Now we're going to do the same one with the trapezoidal rule, and we'll see which one of them is actually closer in estimation. So use the trapezoidal rule to estimate the integral from 0 to 1 of x squared dx using 4 subintervals. Compare the result with the actual value of this integral. Okay, so we are going to look at our trapezoidal rule. So we need to know what delta x is. We also need to know what n is. It says that we're going to use 4 subintervals, so n will equal 4. And then delta x is going to be 1 minus 0 over 4. So our delta x is going to be equal to 1/4. We need to know what our endpoints are for the trapezoidal rule. We do not need to find midpoints on this one. So that is very helpful. So endpoints. We are going to be starting off with, let's draw a picture. And again, I'm going to kind of spread that out a little bit. So from 0 to 1. Oh, that's not right. I need 2. Let's go back. We need to start at 0, 0. There we go. Okay, so from 0 to 1, y equals x squared, and our first endpoint is going to be 0. We're going to break this up into 4 sections. So we've got 1/2 in the middle, 1/4, and 3/4. And our trapezoids are going to be, both points will be touching the graph, both endpoints. So our first trapezoid there, and then another trapezoid here, and so on. So we're going to have endpoints of 0, 1/4, 1/2, 3/4, and 1. So those are all of our endpoints for that. So now our trapezoid, we can go ahead and put this into the equation for a trapezoid rule. So t sub 4 is equal to 1/2, which comes with the equation, times delta x, which we found to be 1/4, times f of the first endpoint, plus 2 times f of the second endpoint, and 2 times f of the third, and so on until we get to the last one, And then this last one we are not going to multiply. We're not going to multiply by 2. Okay, so now we need to find the values for each one of these. So we're going to use our function notation up here. So we can say f of x is equal to x squared. So make sure you know what your function is. So t sub 4 is equal to 1/8. Now if we had a more difficult equation, we could go ahead and use that table values or the table function on our calculator. So 1/8 times f of 0, which is 0, plus 2 times 1/16, so 2/16, plus 1/3. Whoa, that's not supposed to be 1/3. That's a 1/2, isn't it? Okay, that looks better. So 1/4, 16, 2 times 2/16, and then 2 times 1/4 plus 2 times 9/16. Okay, plus 1 squared 1 is just 1. Okay, so then 1/8, and then 0 plus 1/8 plus 1/2 plus 9/8. Okay, plus 1. So 10/8 plus 4, so 14/8. 22/8 times another 8. So that's going to give us 11/16. Alright, I'm going to pause here and look over my work just a second. Okay, I knew I did something wrong. I had to go back and look at it real quick. So, 8 times 8 is 64, then divide 64 by 2, and the top by 2, we would get 32. And that will look much better. Okay, so we end up with 11/32. And then I am super happy with that. So 11/32 as a decimal is equal to 0.34375. Now if you remember when the last example where we did the actual integral of x squared from 0 to 1 dx, that answer ended up being equal to 1/3 or 0.333. So you can see how far off we are with that trapezoidal rule. The trapezoidal rule is a little bit more of an error than the midpoint rule was. Okay, so we will move on to our next example.